Hello and welcome to lecture 14 of the course Computational Complexity. In this lecture, we will introduce space complexity, right? So, as I said at the beginning of the course, the two most important resources that are considered in complexity theory, or in the case of Turing machines, or in the case of computation in general, are time and space, right? So we have been seeing P, NP, polynomial hierarchy, and so on, which are all complexity classes which are based on time. Now we will see complexity classes where the resource under consideration is space, right? So just like we saw time bounded complexity classes, we will see space bounded complexity classes. Some of the classes that we will see are L, NL and P space. Okay, so L and NL are log space and non-deterministic log space. They use order log n space, and P space is the space equivalent of the complexity class P, which is time. So P space uses polynomial space, whereas the class P uses polynomial time, right? So before getting into the actual nitty-gritties of what L, NL, P space, etc. are, let's try to understand what does it mean when we say space usage of a Turing machine. The case of time, time usage is very clear because you just measure time in terms of number of steps that a Turing machine takes to do a certain computation. What is the space usage? So there is a bit of subtlety there, right? So suppose a Turing machine is given, this is a Turing machine tape, okay? And let's say, so as always, n is the usually considered to be the length of the input, right? So the input is there in n tapes, or sorry, n cells of the tape. And as part of the computation, maybe you have to use some extra space, okay? So the part in blue is maybe some extra space that is being used for the computation, right? Right, so n is the red part is where the input originally was, and some more space is being used in the tape, right? And even the inputs where the input originally was, even the red places could be overwritten, right? Because there is no requirement that the input remains as it is, right? Sometimes, like sorting, we don't retain the original order of the input, right? So we may overwrite it. That's okay, right? Because as long as at the end we decide or compute whatever we want to decide or compute, it's all fine, right? So, and let's try to do something naive. Let's say the space usage of a machine is the total amount of cells that is used for the computation in the tape. So suppose this is the tape. So n is the the amount of cells used for the input and some more extra, and the total space usage of this Turing machine is n plus extra, which we will use Sn to denote, okay? Sn to denote. So this sounds reasonable right now, right? Because we use Sn space, which is n plus extra, and we are accounting for Sn. We are accounting for exactly that. So it seems okay. But the problem is that in this model, by the very definition of this model, we have to always have Sn to be at least n, right? Because the space usage always takes into account, or the space usage is always at least takes into account the space required to store the input, and the space required to store the input is n bits or n symbols, right? So the space usage ends up being at least n, right? So now is it correct to kind of assign a cost of n because the Turing machine itself, the input itself uses n symbols, right? So what if the extra very less number of bits is used for the extra, right? So maybe just log n bits is extra space is required for the computation, but just because the input required n symbols, n plus log n is again n dominates log n, so we will say order n space, but then the actual extra space required is only log n. So here the problem is that Sn in this model, Sn always is at least as big as n, which is the input length. So this model is undesirable for this reason. It is okay when the extra space used is more, but when the extra space used is less, this is actually penalizing the machine needlessly, because the extra is what we are interested in, right? So how do we account for log n space, or something that is less than n space, or in general sublinear space, right? Because this space n is always available for the machine. You can always use n space, right? So we want to have n symbols for the input, but at the same time not be able to use that for extra computation. So we will have come up with a separate model. Okay, so the separate model is the following. You have 3 tapes, or maybe 2 tapes, sometimes third tape. Okay, so the first is the input tape, second is the work tape, and the third is the output tape. Okay, so note that the output tape, so there are 2 types of problems that we may have, and most of what we have seen in this course so far are decision problems. If there is a decision problem, we will not be using an output tape. We just have to accept or reject. Decision problem is like, does this graph have a cake leak? Is this graph connected? Is this matrix full rank? Right? So these are all yes or no problems. But it is not problems like what is the square of this matrix, or what is the square root of this number, what is the length of the shortest path from A to B in this graph. Right? So these are all asking us to compute a certain quantity. Right? So these requires an output tape. If it's a decision problem, we will not need an output tape, right? So only when output tape is required, only when you compute a certain function. And further, the input tape will be read only, right? So the input will take n symbols, and that is read only. So you cannot really, the machine cannot use that space to do the computation. So you cannot cheat using that space. And the work tape, you can do anything there. You can read, you can write, you can erase, you can overwrite, all of this. And the output tape, if it's a computing of a function, this will be write only. So just because the output happens to be very long, we don't end up penalizing the machine, right? So if the output is long, if you have to write a matrix product, that itself takes order n squared space, right? So n by n matrix, just to write down, you need n square symbols, right? At least n squared symbols. So, but maybe the actual computation itself does not require that much. So just because output is long, we don't want to penalize the machine. So what will really be accounted for is the work tape. So this is the space that counts. Sorry, space that counts. We don't care about the input tape. We don't care about the output tape if there is an output tape. The only thing that we consider is the work tape usage. So space complexity of a Turing machine is the space used by the work tape. So now we could have the space usage being sublinear, like it could be log n and still we could count that, right? The space usage in the work tape as a function of n. So just like time complexity, so I am not formally writing down the definition. Of course, this is so for this part also you can follow SIPSR chapter 8. There is a chapter on space complexity. You can follow that. I am pretty much following that only, right? Maybe except for some change of ordering in the way topics are presented. So the space complexity is the space use as a function of n, meaning if for over all the inputs of length n, what is the maximum space usage for a certain computation. In the case of, so this is in the case of a deterministic Turing machine. In the case of a non-deterministic Turing machine, we look at, again, just like in the case of time bounded computation, we look at all the computation paths, right? So all the computation paths, and out of all the computational paths on all the inputs of length n, which uses the most space. That is the space complexity. So space complexity in the case of deterministic Turing machine is just the maximum amongst all the inputs of length n. In the case of non-deterministic Turing machine, we also need to account for the multiple branches of computation. Right. So now let me just formally define this notation. This is like analog of d time Tn. So we said d time Tn is equal to all that can be computed with time complexity Tn with a deterministic Turing machine. So similarly, space of Fn, okay, or space of Sn is set of all languages L, where L can be decided by an order Fn space deterministic Turing machine. So if L is decided by an deterministic Turing machine in order Fn space, then L belongs to space Fn. And n space Fn is the same thing. It is analog of n time by n order Fn space ntm. So the only thing that changes is that d changes to n. Right. So if a language can be decided by an order Fn space ntm, then it belongs to n space Fn. Otherwise, if it's decided by order Fn space dtm, it is in d space Fn, and we will not be using the d before d space of Fn. Sometimes we will just drop the d and say s space of Fn, right? Right. So now I have formally defined what is space complexity, and the complexity class is space of Fn and n space of Fn. Now some simple exercises, I can just briefly give you an idea of how to go about attempting these problems. So we saw 3SAT, it's an NP complete language, right? And it's NP complete means it's one of the harder problems in the class NP. Surprisingly, it requires only linear space and deterministic linear space. So the thing is that so how can you show that? You could have a counter. Let's say there are n variables x1 to xn. So there are 2 power n possible assignments, right? So you could have a counter saying which starts with all false, then maybe all false. Instead of, let's say, true false, let us think in 0 1. So you can think of the starting assignments as all zeros, then 0 0 0 0 1, then 0 0 0 0 1 0 1 1, and so on. So you could just have a binary counter kind of thing, and this counter could go through all the possible assignments. So this counter requires order n space, right? Because it's n bits, n variables. So you could just cycle through all the possible assignments, and once you have an assignment, let's say you fix 1 0 1 0 1 or something like that, and then plugging in this assignment and testing in the formula whether it is a satisfying assignment or not a satisfying assignment can be done in linear space. Again, this is not so hard to see, you can work that out. So satisfiability, or at least 3SAT, is in D space n, right? Because 3SAT has a certain structure. Okay. Another language, so it is palindrome, where you have to decide whether the input string is a palindrome or not. This is in order log n space, or deterministic space log n. So this is an example of a language that does not even require n space, so sublinear space, right? So usually order n is referred to as linear. Anything that is less than that is referred to as sublinear. Anything that is more than that is referred to as superlinear, right? So log n is sublinear. Why is palindrome in D space n? Because you could consider the following approach. You could just check with the first symbol, then the last symbol, then the second symbol, then the second last symbol. So all you need is to have a counter to keep track of whether you are in symbol I and n minus I, or n minus I plus 1, right? So you just need a counter to check, to keep track of where you are checking, and then that is the only extra space, and maybe 1 or 2 extra slots, right? So here you saw a symbol A. Now in the like the first symbol is A, so you also want the last symbol to be A if it has to be a palindrome. Otherwise, you immediately reject. So palindrome is an deterministic log space. Now, one further definition. Okay, the class L, right, or sometimes we say L is short for log space, is simply D space of log n, and the class NL is simply N space of log n, right. So L and NL are deterministic log space and non-deterministic log space respectively. Okay, so we saw what is space complexity, we saw D space or space of Fn and N space of Fn, and now we are seeing L and NL, which are specific where Fn is equal to log n. Okay, so now let us see some basic relations between. So we saw space, D space, D time, N space, and we'll see some relations between each one of these. Okay. So the first, D space of Fn is always contained in N space of Fn. Why is this? This is because anything that a deterministic machine can do with a given space, a non-deterministic machine can also do in the given space, because a non-deterministic machine simply has more options or more flexibility, doesn't mean that it needs to use that, right? So just like D time Fn was also a subset of N time Fn, right? So this is the reason, and this also tells us that L is contained in NL, because just as a corollary of this theorem, right? Now let's look at the next result. So D space, so this is result number 1, D space of Fn is contained in N space of Fn. Second is D time of Fn is contained in D space of Fn, meaning if you can do some computation in D time Fn, you can also do the same computation in D space Fn. This may seem a bit challenging. Why is that true? But the reason is very simple. If something can be computed in D time Fn, that means in Fn many steps or order Fn many steps, you could have written at most Fn cells of the tape. So each time step you can only go one step. So at most you would have written order Fn cells of the tape. So the maximum tape usage will be at most order Fn, which means the space required is order Fn, right? So the proof is that the Turing machine, again note that both left hand side and right hand side are deterministic, can write at most one cell of the tape in each time step. So each time step it can only write one cell, right? So the next result is that it relates between N time, non-deterministic time, and deterministic space. So now first we saw deterministic time Fn is contained in deterministic space Ffn. Now we are saying that even non-deterministic time of Fn can be contained in deterministic space, right? So we know that D time Fn is contained in N time Fn. So N time Fn is possibly bigger than D time Fn, but even that is contained in D space Fn. Why? Okay, so let's see what we know about N time Fn, right? So N time Fn means there's a Turing machine, there are possibly multiple possible computation paths, right? Right, so, and we know all that we know is that all the computation paths terminate before Tn steps or Fn steps, right? So this is what we know. This computation tree, the length of the longest path from the root to the leaf is Fn. Now the point is this: we can assume that at the branching factor of the Turing machine, say the branching factor is a constant, let's say it is 10. Okay, so because the branching factor only depends on the only depends on the Turing machine and not the length of the input. So let's say the branching factor is 10, right? So now we can encode the path, each path that it takes. So let's take this path, some path like this, right? So you are saying that first I took the 0th branch, then the first branch, then the second branch, or maybe not second, maybe again the 0th branch, and then maybe the 5th branch, and so on. So I can write the identity of this path as 0, 1, 0, 5, and so on, right? Because I first took branch 0, then 1, then 0, then 5, and so on, where this string is of length fn, right? So each path that the machine takes can be encoded by an fn length string, right? We can keep track of. So now all that we need to do is to, so you have a non-deterministic Turing machine or non-deterministic Turing machine that runs in fn time. We need to, in a deterministic sense, how do we simulate this, or how do we check all the paths, right? Because we need to simulate it with a deterministic space Turing machine. So what we can do is we can have a counter. So here we are saying 0, 1, 0, 5 is the identity of this path. So you can have a counter that generates all the length fn sequences, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 3, so on, right? So these are all possible paths, and for each of these paths the machine can execute this computation. So it can check for if it takes 0th path, first path, 0th path, 5th, 0th branch, first branch, 0th branch, 5th branch, so on, does it lead to accept or not? And if any of these paths accept, then the machine also accepts. So the deterministic simulation is simply check out all these paths, all these different branches. So you basically do an exhaustive search in this computation tree, and this does not require more space than order fn, right? Because you are not maintaining the entire tree, you are just checking each path by path, right? And this each path is encoded by an order fn long string. So the extra space required is also order fn, and each computation is also order fn because it's also order fn time, so it's also order fn space. So n time fn is contained in DSPACE fn. Non-deterministic time fn is contained in deterministic space fn. So now what the previous thing that we saw also follows from this. D time fn is obviously contained in n time fn, so it's also contained in DSPACE fn. Okay. Now what else? Now let us see. So we saw time complexity classes. How is it contained in space complexity classes? Now we'll see the opposite. How is DSPACE fn contained in d time of d time, right? So what d time of what? So we already know that d time fn is contained in DSPACE fn, right? So the same amount of time, same function, time is contained in space. For the same function, is space contained in time? Possibly not, because we already saw that sat is in DSPACE n, so it is in linear space. If we know that DSPACE fn is contained in d time fn, then that would imply that sat is in d time n, which would mean that it is in polynomial time, which we know is not, which we do not know as of now, right? So it turns out that what we know now is that DSPACE fn is contained in d time 2 power order fn. So it is an exponential time that much, right? Why is this the case? So DSPACE fn is contained in d time 2 power order fn. So let us first count the number of configurations of the DSPACE machines. Right? So DSPACE machine, there are multiple components to the configuration. So one is the input is fixed. So the input is read only also. So the input cannot change, right? But the work tape has fn space, and each of these fn space could contain any symbol, and let's say sigma is a set of alphabet. So size of sigma is a number of symbols. So there is sigma power fn ways to fill up the work tape, multiplied by, there are two heads, one in the input tape and one on the work tape. So the input tape has n locations, so because it's only the input, so the head could be in any one of the n locations, and the work tape has fn locations, so the head could be anywhere in the fn locations. Finally, the last part of the configuration is the state. So let's say q is a set of states, so size of q, right? Now let us say this is, so now the sigma I can write as 2 power c1 for some constant c1, 2 power c1 fn multiplied by n times fn times size of q. Size of q is also a constant, right? Number of states is a constant. Now I can simply write this as, this is less than or equal to 2 power c2 of fn, okay, because n is, so suppose fn is at least log n, then n can be written, n is dominated by 2 power fn, and fn is also dominated by 2 power fn, and q is a constant, so that is also dominated by 2 power fn. So all we need to do is to change the constant here from c1 to c2, slightly higher constant. So the number of configurations of the DSPACE machine is 2 power order fn, right? So this is 2 power order fn, order fn configurations. Those are the number of configurations of the DSPACE fn machine, right? Again, here we assume that fn is log n, at least log n, and this is an assumption that is helpful to make throughout this part, not this lecture, but this part where we talk about space complexity, because just to read the input in a reasonable manner, right? So the input is of length n. Just to read the input, we will require the need of some counter which keeps track of where we are, and that counter has to be at least of log n bits. So if we are not even allowed log n space, the kind of things that we can do are extremely trivial and they are not very interesting. So throughout we will assume in the case of space complexity that fn is at least log n, and it's okay because this assumption is not penalizing us much. When this is not true, then the classes that we have are not very interesting. Okay, so we'll keep this assumption throughout. Okay, so now we know that there are 2 power order fn configurations, right? So now let's say there is a starting configuration. Let's say this is the starting configuration, this red one, this is the starting configuration. It's a deterministic space bounded machine, so it's followed by another configuration, it's followed by another configuration, and we need to keep going like this till we hit accept or reject, right? The computation ends when you reach accept or reject. But how many steps should this computation go? So note that there is another possibility. Instead of accept or reject, it may come back to some earlier configuration and then it could just keep looping. But how do we check that? Again, we probably cannot check that. But what we can do is to count the number of steps that we have done, how many configurations that we have crossed. This is because we know the number of configurations is bounded by 2 power order fn or 2 power c2 fn, and if it is looping, we will just terminate after 2 power c2 fn, because then it is never going to come out of it. If it loops, it has to loop before 2 power c2 fn, right? So because there are only 2 power c2 configurations, so if it comes back to another configuration, it will happen. Or if you have crossed 2 power c2 fn time steps and you are still not done, that means you are looping, you have come back to some earlier configuration, right? So all you do is you just run the Turing machine up to 2 power order fn steps. So instead of order fn, maybe you can make it more precise, 2 power c2 fn or whatever, on the configuration graph of the DSPACE machine. right? And if it accepts by then, good. If it does not accept by then, that means it is not going to accept any longer. If it rejects by then, that's also fine, right? So this simulation will take at most 2 power order fn steps. That's why deterministic space of fn is contained in deterministic time 2 power order fn. Again, when fn is at least log n, and we will throughout be making this assumption. Again, now if we set fn to be log n, we get that L is the left hand side is 2 power, sorry, d space fn, so d space log n, which is log space L, and the right hand side is 2 power constant times log n, d time 2 power constant times log n, which corresponds to p, right? Because 2 power some constant times log n, this is nothing but n power some constant, right? So d time 2 power constant log n is simply d time n power constant, which is the class p. So we saw d space and n space. D time, how is it contained in d space? D time, how is it contained in n space? Then we saw d space, how it is contained in, sorry, d space, how it is contained in d time. Now we will see n space, how is it contained in d time. So n space is potentially bigger than d space, right? Because we already saw d space is contained in n space. Turns out even n space of fn is contained in d time of 2 power order fn, right? So let me just fix my handwriting a bit. D time of 2 power order fn. So this is the same right hand side that we had for d space as well. So it turns out that for n space also the same right hand side suffices. In this case, so again the configuration bound is the same, because the number of configurations does not depend on whether it's a deterministic Turing machine or a non-deterministic Turing machine, right? All it is a snapshot of where the Turing machine is right now. It is not something that is indicative of the dynamic movements of the Turing machine. Right? It's just a snapshot of where the Turing machine is now. So the number of configurations is 2 power order fn. But however, in the case of deterministic time machine or deterministic space machine, we know that every configuration has a single unique successor. Starting configuration gives rise to C1, C1 and C1 gives rise to C2 or something like that, right? It goes like that, and so we just need to execute that. In the case of n space machine, we could have many possible, like we could have a branching factor, right? The starting configuration could have 10 possible children, successor configurations. Each successor configuration could have its own 10 possible successors. So there is a lot of branching possible. So suppose the branching factor is b, right? For each each configuration you could have b successor configurations. Then the total number of like the paths that we have to explore could be as large as b to the power 2 to the power order fn, which is something humongous, right? So this is not something that is desirable, and our right hand side we just have 2 power order fn, there is no b there. Okay, so why is that? That is because the actual number of configurations is simply 2 power order fn, just that if we have 2 power b power 2 power order fn computation paths, it must be the case that many of these paths are reusing the same configuration. So the actual number of configurations is only 2 power order fn. So, but then many times you are probably jumping from one path to the other, and all these kind of crisscrossing must be happening, right? So now let us try to draw it in a different way, where we just have one in this picture over here, in this picture that I am circling with green. We draw each configuration only once. We have the starting configuration for a specific input. There are a bunch of successors, and it's possible that two successors have the same share a successor, right? And anything like that, and maybe even this kind of things are possible. From the second state, you may come to the something like this, right? All these things are possible. It's a non-deterministic machine, so there could be looping on some parts, but there may not be looping on other parts, etc. All we are interested in, is there a path from the starting state to the accepting state in this configuration graph? Is there a path from the starting state to the accepting state in this configuration graph? We know that, so each node, each vertex in this configuration graph is the configuration. So we know that this graph has at most 2 power order fn vertices, and there are two designated states or configurations. One is the starting state, starting configuration, and one is the accepting configuration. We want to know whether there is a path from the starting configuration to the accepting configuration, right? And this is a directed graph. How do we do this? This is something that should be very familiar to all of us, right? So what we do is, we could use any traversal algorithm, right? So let's say we use breadth first search or depth first search on this configuration graph, and this runs in order v square time. Let's say you use the adjacency matrix representation. It runs in order v square time, where v is the number of vertices of this graph. So it is 2 power order fn is the number of vertices, so it's square of that. But again, there is an O here, so it just, the square just can be absorbed by the O in the exponent. So in this outside O is kind of pointless, it's not required. So 2 power order fn time. So that's how even n space of fn is contained in d time of order fn. So if you plug in fn to be log n space of log n is nothing but nl, non-deterministic log space, and d time of 2 power order fn is nothing but 2 power polynomial. It is d time of polynomial, which is p. So what is the exact problem that we tried here, or that we had here? So you are given a directed graph, and there is a specific vertex, and there is another specific vertex. Is there a path from the first vertex to the other second vertex that I specified? So this problem turns out to be somewhat important when studying space complexity, and we will call this problem as path. Path is simply given a graph, a directed graph, and two vertices s and t. It is asking whether there is a path from S to T, a directed path from S to T. So, right. So, is there a sequence of vertices or edges such that you can start from S and you can somehow reach T? This is path. So it's a decision problem, and so I'll stop after this. One small exercise is, show that path is in NL. This is a non-deterministic log space, right? So we can only use logarithmic space, right? So we cannot, you cannot do the breadth first search in the exact same way, because you cannot be maintaining a visited marker and all that. Right? We have to be more careful with that, right? So show that path is in NL. So just because if you maintain visited markers in each node, then that is itself order n space required. So you don't have that space. Okay, so show the space usage. So what I'm saying is show the space usage in the proof, right? And log space reductions, I think we will see it in the next lecture. So just to summarize what we saw, we saw the space complexity model, which is the input tape, work tape, and output tape. We formally defined space complexity classes DSPACE of Fn and NSPACE of Fn. We said L is DSPACE of log n and NL is NSPACE of log n. Then we saw relations between the space complexity classes and the time complexity classes, the generic classes. DSPACE of Fn is contained in NSPACE of Fn. The time of Fn is also contained in DSPACE of Fn. The n time of Fn is also contained in DSPACE of Fn. So this is time classes contained in space classes. Then we saw space classes contained in time classes. So DSPACE of Fn is contained in the time of 2 power order Fn classes. Sorry, 2 power order Fn. So if you have the same space, or if the time of Fn is contained in DSPACE of Fn, but the space of Fn is contained in the time of 2 power order Fn. This also implies that L is contained in P, right? We already saw P. And the non-deterministic equivalent, so n space of Fn is contained in d time of 2 power order Fn. Right? So even if you have n space instead of d space, even that is considered d time of 2 power order Fn, which implies that NL is contained in P. And finally, we defined the language path, and I asked you to see why it is in non-deterministic log space. And I think with that, we'll stop this lecture. Thank you.